Okay, thank you very much. Yeah, I'd like to echo the calls for clapping for the circuit. This is really wonderful. Oh no, I hope this doesn't keep happening. Yeah, and I'd like to also say how wonderful it is that the talks are available asynchronously, because I certainly would not be able to attend most of them. So today I want to talk to you about certain issues which come up when we look at quantum systems with infinitely many degrees of freedom. And I want to show you that there are circumstances in which we can plausibly contemplate the idea that infinitely many simultaneous measurements might be made. And this is something which hasn't been thought about, to my knowledge, in quantum theory very much. And I'll argue for you that the most plausible result of this, at least in the cases I'm going to look at, is that the Hilbert space can wind up being modified. And I'll be precise about what that means. Now, when I talk about infinitely many simultaneous measurements, I am not suggesting that we have a laboratory populated in any ordinary sense with infinitely many experimenters, or even one experimenter with infinitely many desires. But what I do think is very possible is that, you see, nature is probably frequently making measurements. Measurements are not our physical processes. I find it completely incredible that they should only be made by human actors, or only on Earth. They're happening all the time. But we do not have a theory of when measurements are made. Quantum theory tells us how to treat a measurement, given that it is being made. We apply the Born rule. And I think this is a really an overwhelming gap in quantum theory that prevents it from being a complete dynamical theory. We do not have any objective way of saying under what circumstances a measurement is made. Nature is presumably making that. And that's what motivates this talk. So let me start by saying what I mean by a quantum system with infinitely many degrees of freedom. This is not quite straightforward, but for the purposes of this talk, we can give a pretty good answer. So it's not just that you have an infinite dimensional Hilbert space, because even a particle, an ordinary quantum one particle on an interval, has an infinite dimensional Hilbert space, but we don't usually think of it as having infinitely many degrees of freedom. So what is the concept that I'm trying to get at here? Well, let me tie this in with how I want to look at the problem. I told you we were going to be thinking about changing Hilbert space. So I want to think of constructing any given quantum theory in two stages, where we only get to the actual construction of the Hilbert space in the second stage. The first stage is to specify the dynamical variables, like the p's and the q's, or something like that, of the canonical variables, and their abstract algebraic properties, which might be like the canonical commutation relations. So we can think of this as an algebraic system similar to the way we would specify a group by giving a multiplication table. There is not yet any representation of these operators on a Hilbert space. That is important to achieve, but that has not yet been done. The second stage is the construction of a representation of this algebra as self-adjoint operators on a Hilbert space. So basically, we think of quantum systems as described by certain quantum dynamic variables. In quantum mechanics, the p's and q's. In quantum field theory, it would be fields phi and their velocities pi. Or for, say, a spin chain, there would be the Pauli operators. And these are subject to certain algebraic rules, which might be the canonical commutation relations, they might be the spin relations, what have you. And now when we really want to describe a particular quantum system, we must not just choose this set of variables, okay, but we have to describe a Hilbert, we have to describe a representation of them on the Hilbert space. And what's going to be distinctive about systems with infinitely many degrees of freedom is that we need infinitely many of these basic variables, these basic quantum variables, to generate the algebra of observables we're interested in. So in a quantum mechanical system, we have only finitely many p's and q's. In a finite system that spins, we have only finitely many Pauli operators. But in a field theory, we have an infinite family of phis and pi's, and in an infinite spin system, we have an infinite family of spin operators, one set sigma x, sigma y, sigma z for every site. Okay, so let's look at some examples of this, which are familiar. And the technicalities, most of the technicalities are not important. I'll just explain in physical terms which ones are. So if we look at the, first of all, the case of finitely many degrees of freedom here, and we take the canonical commutation relation, then the Stone-von-Neumann theorem tells us that all irreducible representations are unitarily equivalent, so there isn't really any significant choice in which representation to construct. But in the infinite dimensional case, there's a theorem due to Schale which says, yes, indeed, there are very many inequivalent representations. And in physical terms, this oversimplifies slightly. What distinguishes these are the infrared and ultraviolet asymptotics of the two-point functions. So different representations of the CCR will give rise to different physics in this sense. And that's the sort of thing that's going to come in for us. So let's look at the canonical example of the construction of a Fock space. So we start from the canonical commutation relations. That's the algebraic part. And then we start bringing in an additional choice, which determines which representation we construct by appealing to Poincare invariance. And we use that to split the field operators into annihilation and creation parts. And then we assume, and this is also part of the physical input, that there's a unique invariant normalized vacuum state annihilated by all the annihilation operators. And once we have that, we can construct the irreducible representation by just following our noses. Anything of the form a certain number of creation operators applied to that state is supposed to be in our Hilbert space. Okay, and we can deduce the norms of all of these states by applying the canonical commutation relations, and we can build up the entire space this way. Okay, and that's the usual construction of a Fock space. Now, I want, for reasons which are going to become clear in just a minute, also to look at an infinite spin chain. And this is not going to be the thermodynamic limit. This is going to be where you consider larger and larger finite spin change. This is going to be, we're going to assume that this is infinite from the beginning. Oh no. There we go. So in this case, we have a bunch of sites labeled by alpha, and let's say each site, there's a two-dimensional spin up, spin down. I really just care that there are two states here. And so we have Pauli operators on each side. Then by analogy with the Fock construction, we could construct a Hilbert space by assuming that there's a state which is, say, initially all down with respect to the Z operator, and allow other states which are constructed by applying finite sequences of spin operators on this. Okay. we can build that up to a Hilbert space. Okay. So this follows directly analogously to the construction of the Fock space. Okay. And these two-state systems are not just analogous to the Fock space, but we can actually regard these as being certain degrees of freedom of a quantum field theory, just some particular degrees of freedom of an underlying quantum field theory, as you'll see in just a moment. Okay, so this representation that I've described does depend very much on the generating state, which I took to be all the sites in the down condition. And other choices of generating state will be most often orthogonal to all vectors in this Hilbert space that I've constructed if the factor states are distinct, point in different directions from the down state for infinitely many sites. So then let me bring in a very physical, simple model. Let's suppose we have infinitely many separated atoms on some time-like hypersurface. And you can think of this as being something that might very naturally occur in a cosmological model. Okay. So, and each atom will just care about two of its possible states. It could be more complicated, but we'll just care about two of its possible states. Okay, so these are really states of a particular quantum field theory, but we're simplifying. And let's suppose that for some cosmogenic reason, each of the atoms is initially in some state, which without loss of generality, we can suppose is the down state. Okay. And then we can apply the previous construction and we get a Hilbert space. But now, supposing there's an observer near each atom, and that observer measures the X component of this spin. So having done that, the atom alpha will be projected into an eigenstate of the X component, which will be a superposition of the up and down Z components. So the results of this will be coded in a set of signs, plus or minus, S is plus or minus for each alpha, okay? And the resulting state will be this product of this new set of initial states. But what I argued for you a few slides ago is that that's going to be generally orthogonal to the initial state. And in fact, it's easy to see that that's true because if I compute the amplitude to go from the initial state, which was all downs, to this new state, okay, these guys go to 0, and I have the product of 1 over the square root of 2 infinitely many times, which will be 0. So the interpretation of this is that this new state will generate a representation of the dynamical variables, okay, a Hilbert space, but this new space will be orthogonal to the original one. Okay, there's some interesting points from this. Okay, each particular outcome has probability 0. Okay, each particular configuration of signs has probability 0. But of course, you can have sets of outcomes which have finite probability. For instance, all those which have the property that the first atom is in the up state. Okay. There are also sets of outcomes which have ill-defined probability. They're so-called Vitali sets. And almost all of the outcomes correspond to uncomputable maps from that family of sites to the sequence of signs. Now, this particular example suffers from what you might regard as a serious defect in that no finite observer could verify this change of representation with mathematical certainty, because our finite observer would be located at a particular event and her light cone would cut this initial surface in a compact region, which would include only finitely many of the atoms. On the other hand, it's true that later and later observers could acquire increasingly compelling evidence for the change in representation. Could there be, though, a circumstance in which the results of infinitely many different commuting measurements were known by one finite observer, say an observer at this event here in space-time? So if we don't have energetic restrictions on the measurement possibility, it's easy to come up with examples like this, because you can consider on a space-like hypersurface here, different families of different space-like separated field domains in which you might measure field properties. The field operators in all of these commute, so they're independent. And the results can at least be, in principle, be known at the vertex. Okay. On the other hand, as we travel down this space-like hypersurface, we need increasing boosts. So the energies involved presumably become unbounded. So this very simple idea doesn't work. But I want to just outline for you how you could construct at least in principle, something which looks like it does have a chance of requiring only finite energies and still measuring infinitely many commuting variables. Okay, so what I want to do is look at the S-wave sector of massless Klein-Gordon theory, which is just to make the problem simple and to take advantage of its two-point function, which is very easy to analyze. And the field operators there can be reduced to those of a two-dimensional field theory. And then it turns out that if you just consider averages of these at a fixed radius of over different time intervals, you can arrange for all of these to commute by taking sufficiently separated temporal intervals going back further and further in time. And presumably, because these extents can be made, very long in time, for these field averages, the energetics can be made as small as possible. This is a very rough argument, but since we don't have a good theory of the energetics of quantum measurement, this is the best I can do at the moment. So using a construction like this, it's not very hard to contrive an example where we seem to be able to get infinitely many measurements, all knowable at one instant of time. Okay, so that's it. That's my talk.
Right, that's amazing. Thank you so much, Adam. Let's thank Adam for the talk. Are there any questions from the Zoom audience here? Okay, if not, then Adam, I'm not really sure how to understand the measurements and well the setup that you've described there in a relativistic setup, I guess. So would you mind speaking a few words about this? Saying a few words about this?
So the relativistic issue comes up in the question of causality, and related to that, the question of how much energetics, what energetics are needed for quantum measurement. So in this example here, although according to quantum theory, you have all these different observers making these different observations, and that's somehow happening all at this t equals constant hypersurface. it's not that can't be known to any finite observer, because presumably the observer can only detect things in their causal past. So at any one point, maybe this really does happen in cosmology. Maybe there are these states that are created in one way and then undergo these measurements. At any one point, an observer looking backwards would see more and more of these states, which she might find are just always in this either in this particular pattern. Okay, and then you would get increasing evidence that the state had made a transition to this new Hilbert space, but you wouldn't know for sure because you'd only investigated at any one point finitely many degrees of freedom.
I see. No, that's amazing. Thanks a lot for the answer. So then let's thank Adam again. Sorry, Michael. Do you have a question or?
Yeah, I have a question.
Yeah, sure. Go ahead.
Yeah, about the spin model that you discussed.
Yeah.
You mentioned at the beginning of your discussion of it that you had a finite number of spins first, which you then made them all point down, and then I just wanted to understand, did you send was it important in the argument that you have to send all the number of spins first all the way out to infinity, then you do the measurements on all the spins, and then you get a state which is not orthogonal to the
number of spins. The number of spins is infinite from the beginning. This is in contrast to the way people.
Okay, I thought you mentioned that the number of spins was finite at the beginning, but maybe I misunderstood.
No. So it's actually essentially different from the way people usually think of infinite spin chains, where they think of a thermodynamic limit. This is a quantum system, and it's most plausible physically from a cosmological point of view. If you imagine that somehow the universe was created with this distribution of atoms, and for some reason their spins were mostly all one, their states were really mostly all of one sort. And then we imagine that later in the universe some other measurement of the atom states is made.
I see. So I guess I'm interested in this from a condensed matter perspective,
yeah,
where we might have 10 to the 23 spins. Is that like enough to be still like? I mean, it's still. I might as well consider that infinite, and there.
Yeah. So I mean, so in a practical sense, that might very well be more than enough, right? Just the way we are very happy to use canonical ensembles to describe things which are not actually infinite. To define it, you get into the question at some point of what are the other physical effects that are competing, and do they dominate the issues in the finite, in the question of your system being really large versus infinite? Are the other physical effects so big that question is just not relevant to me?
Amazing. Thank you so much, Adam. Thanks for the question, Michael. So let's thank Adam again.